I think I'm recording now. Okay.
Yeah, just while we wait, our substantive Vice Chancellor is on medical leave at the moment. And so that's why you won't be attending.
Oh.
Okay.
Hi, Michael. Hello.
Hello.
Good evening,
Oh,
everyone.
sorry.
Ah, that's James Chibuse, who's at Northwest University, young astronomer who's just published a paper in Nature. So welcome, James, I know you're in Mozambique at the moment. I just introduce you quick. At the top is Professor Ogu, our new Deputy Vice Chancellor for Research, Development and Innovation. You know Mike, he's a legend, and there are two Mikes, they're both legends.
Yeah, good.
Welcome, James.
Thanks a lot. Thanks. How are you doing, Greg?
We are very good. We are waiting for you to come and visit us.
I will at some point.
Okay, good stuff. Okay, James, we hope you enjoy it.
Thank you.
Okay, I see we have 44 people now, and it's 2 or 3 minutes past the hour. So without further ado, I'm Mike Bode. As some of you know, I'm a visiting professor at Buist, emeritus professor here in Liverpool in the UK. The first thing I have to do really is to say that if you can put yourselves on mute, apart from when we get towards the end, when questions and answers will be taking place. Without further ado, I will ask Professor Abraham Ogwu, who is the Deputy Vice Chancellor for Research and Innovation at Buist, to say a few words of welcome. Professor Ogwu.
Okay, thanks, Mike. The Deputy Permanent Secretary in the Ministry of Tertiary Education, Research, Science and Technology, Dr. Kekuni Baipuledi. Our Vice Chancellor unavoidably is not here. The Deputy Vice Chancellor, the Acting Vice Chancellor, David Katsi, the DVC Academic Professor Shemang. Today's guest speaker, Professor Michael Kramer from the Max Planck Institute for Radio Astronomy in Bonn, Germany. The moderator for today's webinar, of course, Professor of Astrophysics, also at Buist, Professor Michael Bode, members of the Botswana International University of Science and Technology academic staff and students, members of the Astronomical Society of Botswana, all distinguished invited guests, ladies and gentlemen, I greet you all. It is indeed a great honor and privilege to welcome all to this special webinar session hosted by Buist. I wish to especially extend a warm welcome to Professor Michael Kramer and thank him for honoring our invitation to speak today on the Square Kilometre Array, SKA, challenges and opportunities in science and beyond. Moderator, we are delighted at Buist to lead the coordination and the collaboration of the Square Kilometre Array, the African VLBI network, SKA AVN activities in Botswana, as mandated by the Ministry of Tertiary Education, Research, Science and Technology. We are alive to the fact that SKA is a mega project to build the world's largest radio telescope to explore the universe that is both complex and multinational. Moderator, let me take this opportunity to update the audience on the progress of the AVN project, which is a precursor to the SKA Phase 2. BIOST is at an advanced stage to finalize the location of the AVN dish on campus, pending a confirmatory radio frequency interference survey that will be done by the Botswana Communications and Regulatory Authority, BOCRA, in collaboration with the South African Radio Observatory, SARAO. In the next 6 months, the following milestones will be achieved: environmental impact assessment and geotechnical surveys, construction of access road, provision of power, and provision of fiber connection. BIOST is taking the development of space and technology with optimism and is driving the change. In the 5-year horizon, we would have a national optical observatory, including a planetarium, a HIRAX radio facility, Space Science Center of Excellence that will constitute an astropark. With these remarks, let me take this opportunity to once again welcome Professor Kramer from Bonn, and believe we shall make good use of his enlightened views. Pula. Michael, over to you, please. You're all welcome.
Thank you. Thank you very much, Professor Ogwu. I'll now introduce our speaker, Michael Kramer, who is the director of the Max Planck Institute for Radio Astronomy in Bonn. Michael and I have known each other probably since his early days in Manchester, probably 20 years ago, Michael. Gosh, we were young lads in those days. Michael is actually a native of Cologne in Germany, and he did degrees in physics at Cologne and Bonn, then did a PhD in Bonn. He became a staff astronomer in the institute he now heads, and then a research fellow at Berkeley. He joined the University of Manchester in 1999 as a lecturer and rose through the ranks very rapidly to become not only professor, head of the Pulsar group, associate director of Jodrell Bank, one of the world's premier radio observatories, which is only literally down the road from here, a place I know very well. He's been a member, or is a member actually, of the Scientific Council of the European Research Council, one of the world's premier funders of research across the board, across science, etc. He's also currently president of the German Astronomical Society, so he was elected in 2020 to that by the fellowship of the society. He's won many awards and prizes in a very distinguished research career, focusing on pulsars, but also is very active in other areas of radio astronomy as well. He's a recipient of the Herschel Medal of the Royal Astronomical Society, one of the UK's premier astronomical awards. He's co-lead of the European effort of the Event Horizon Telescope, which many of you will remember the headlines a couple of years ago now about the image of the black hole, first image of a black hole in M87, distant galaxy, which made not only international headlines, but also gained that collaboration with Michael as one of the co-leads, many international prizes. Well, Michael is one of the smartest, nicest, most dedicated people I know. It's been a pleasure to know him all these years. And without further ado, I'll ask him to give us a talk tonight on the Square Kilometre Array, challenges and opportunities in science and beyond. Michael.
Thanks, Mike. I'm not sure what to say, but I very much appreciate the words, that's for sure. I would rather stand in front of you because I still can't get used to the feeling that I actually should sit while I give this talk. But let's see how it goes. And there's also, of course, a lot of people who are quite aware of the SKA and so could give that talk as well. But I'll try to do my best and give you my impression about this fascinating project. And I'm going to share my slides now.
Mike, before you just continue, just for protocol, who joined now while we were talking, I would like to welcome the DPS of the Ministry of Tertiary Education, Research and Science and Technology, which Professor Ogu did mention. Also, there's the Director of the Department of Research, Science and Technology, Mar Tamai. And I see we also have, I think, the Turkish ambassador to Turkey in Botswana, also joining us. So welcome.
Well, thank you very
Also,
much.
our Vice Chancellor is also joined us.
And Professor Totolo, yes.
Yes.
Thank you.
Excellent. Well, I feel very honored that you want to listen to me. I hope I don't disappoint you. Yeah, without much further ado, let's see what I'm going to share with you. I hope you can see my slides. This is probably one of the most quoted words right now. But if you don't, please let me know. What you see here is an artistic impression, obviously, of the SKA, the Square Kilometre Array, which is, as we'll hear more in detail, built on 2 continents. And so they're really in this picture merged Africa and Australia together as it was once in a long distant past. And here it is for the purpose of the SKA. So let's unveil the universe with this particular interesting project. And just let's get a step back and really think about this universe that is governed by Einstein's laws of gravity. And it's an extreme and interesting place. And we try to decipher the laws that govern that universe just by sitting here on our planet, just by receiving photons or gravitational waves or neutrinos these days, but just sitting here on our planets and really trying to understand the if someone can and trying to understand the universe as we see it, and literally by seeing it. And I really like that quote from Richard Feynman, who said that we do not know what the rules of the games are. All we are allowed to do is to watch the playing. Of course, if you watch long enough, we may eventually catch on to a few of the rules. And the rules of the game are what we mean by fundamental physics. And as humans, we have watched this game for thousands and thousands of years, and we're still trying to figure out. I don't know if can you mute perhaps if you're not muted yet? That would help me. Thank you. So anyway. And when we think about the universe nowadays, we think about the universe as a whole, how it actually all began and where it may lead. And this is one famous kind of graphics who tries to encapsulate that. We have, let me try to switch on my laser pointer if this works. We have basically the beginning with a Big Bang about 14 billion years ago. Then there was a rapid expansion of the universe that we don't quite understand, but we call inflation. Then the universe was basically hot, and then it cooled down and nothing existed apart from hydrogen, basically. We call that the Dark Ages. And then eventually the first stars and galaxies and everything formed. And now we reach sort of 14 billion years later what we have today. And that's a pretty good impression, but just looking from our planet and look out into the universe. But it's not, we don't understand it all. We don't understand inflation. I already mentioned this, but in particular also, we don't understand the recent accelerated expansion of the universe that is attributed to something we call dark energy. And I'll come back to that. So this is just one of the unsolved questions that we are trying to answer today and tomorrow with our new instruments. And so some of the big questions that astronomers and physicists alike want to address are listed here. How do planets form from disks of stars and gas? Is there life somewhere else in the universe apart from Earth? And what are the conditions to create it? How do galaxies evolve in cosmic time? How did the structure form that we observe in the cosmos today? And how does it continue to roll out? What is dark matter? What is dark energy? I'll come back to these particular questions later on. And what are the early phases of the cosmos like? And how and when did the universe ionize? I'll come back to that question to explain it later on. And what is the origin of matter? As basic as this. And of course, what really happened just after the Big Bang, and what are the properties of inflation? So these are really big questions because they involve actually not only the beginning and the fate of the universe, but really all the laws that govern it. My favorite topic is actually looking at gravity. And so I also have my special list of gravity questions. And gravity is important. We know this because Hollywood make movies from gravity. And so the big questions maybe in that movie was whether Sandra Bullock survives the fall from the sky, or we know Interstellar, and here the big question was whether the hero is reunited with his family and his daughter. But really the questions that we want to answer is, was Einstein right? Or as the Australians seem to answer it, was he wrong? So my questions here for gravity is, what are the properties of black holes? And we have learned quite a bit, but we haven't answered all the questions. What are the influences of black holes on their galactic environments, and how do they both evolve? What are the properties of neutron stars? We still haven't answered all those questions. In particular, what is the equation of state if you try to compress matter to very extreme nuclear densities? What are the effects of strong gravitational fields on our observables? And what properties do gravitational waves have? We have detected them on Earth, but we haven't answered all these questions. And so the question is, was Einstein's description of all the above correct or not? So these are questions. As an astronomer, we of course want to answer them with new instruments. And so we have learned in the last maybe 30 years or so, 40, 50 years, that the answer to these questions is probably not likely to come from just one instrument, but actually by combining the information across the electromagnetic spectrum, plus now gravitational waves, neutrinos, and other messengers. We call it really multi-messenger astronomy. And so, for instance, if you want to look at M31 Andromeda Galaxy, you may see this like this in the optical, but at very high energies or very low energies, it looks sometimes completely different. And really to understand the properties of the galaxy, you should really encapsulate all the information that you can get. And so not a single facility will probably answer these questions, or these questions are listed, but one or the other can contribute more than others. And so when we talk about these instruments that come up in the future, basically we have new very big optical telescopes. The James Webb Space Telescope, for instance, will be launched hopefully very soon. We have the ALMA array in Chile. We're looking at millimeter and submillimeter. And at the lowest part of the electromagnetic spectrum, we have the SKA. The SKA will look at wavelength from centimeter to meter range and will contribute to the answers of these questions that I have mentioned. And I'll try to explain at the end of my talk how the SKA may play a role here. But the reason why the SKA can play this role is because radio astronomy is special. It's quite different from the rest of the astronomy parts and the other parts of the electromagnetic spectrum because of the photons we observe. First of all, we can synthesize big telescopes by putting them across the whole Earth, combine them, the data signals to form a telescope really as big as the Earth and with satellites even beyond. And that really produces the sharpest images of all astronomy. We can also receive lots and lots of photons. They may be low energy, but they're actually coming from very energetic and compact objects sometimes. But importantly, there are lots of them, and we can easily copy, multiply, and combine them with our techniques in a much better way, much easier way, I should say, than with other parts of the electromagnetic spectrum. In addition, radio light is not blocked by dust. It basically goes through everything. And so we can look, for instance, right into the galactic center, and we are not bothered by some dust clouds blocking our view. And of course, we sometimes see completely different processes that are just not visible at any other part. So as an example, I like this picture. I think Peter Wilkinson produced this first long time ago. This is a combination of galaxies seemingly unrelated on the sky. That's what you would see in the optical. But if you actually look at in the radio in the light of neutral hydrogen, the most common element that we have in the universe, you basically see big streams of gas connecting these galaxies with each other. And if you wouldn't know about these gas streams, you would probably misinterpret the data that you see at other parts of the electromagnetic spectrum. So really, again, understanding these galaxies, you need to get all the complete information, in particular that of the radio, which gives you the light. And so the SKA is basically an instrument that helps you to trace the evolution of the universe in the light of its most common element, namely hydrogen. And this is the only equation I want to show you today, but it basically describes the most important equation of radio astronomy. It describes the sensitivity of a radio telescope. So on the left-hand side, you have the sensitivity, the smaller, the better. So the smaller the signal you can measure, the better. Then on the right-hand side, you basically have the size of the telescope, which is this A here. You have the noise temperature, as we call it, of your receivers. The lower, the better. The bigger the telescope, the better. And you have some dependency in the square root, which is the observing time and the size of the bandwidth of the electromagnetic spectrum that you can capture right at once. So in order to make this number small, you have not much choice. You can try to make the system of your receivers the smallest temperature as possible, but in fact that's impossible already because our receivers are already so good that they're working at the quantum limit, and so therefore we already have the technology reached to make this low as possible. We can't improve on this anymore. So the biggest improvements, therefore, you can only get by making your telescope bigger to increase G, the gain, or you increase the bandwidth that you can digest with your system, or you can try to stare at one place as long as possible. And the SKA tries to eventually improve on all these numbers by increasing the gain, by looking at a larger fraction of the bandwidth of the electromagnetic spectrum, and by having tricks to observe longer per position on the sky by looking at a larger fraction of the sky at the same time. Now let's go through that one by one. The SKA wouldn't be possible, and lots of our observations today wouldn't be possible, without a revolution that has really taken place in the last 10, 15 years. Basically what we have done, we went completely digital. We try now not to have just analog receivers, but actually the ability to sample, digitize, and process them with commodity computing hardware, for instance, graphics GPUs or the FPGAs, right at the receiver. And that really going to the digital domain right at the front really opens up even more processing avenues than we had before. That means you can try to get cheap collecting area by replacing maybe expensive metal hardware with a lot of electronics and software. That comes as a price when we talk about data rates, but I'll talk about that later on. The other way is we can build radio cameras, really multi-pixel, many pixel cameras that can look at a larger portion of the sky. We call it the field of view, and even sometimes look at completely different directions at the same time. So really we're trying to replace sometimes the classical parabolic reflector with some receiving elements. And you can put them elements either on the ground or mount them on a telescope. And here is an example. When you put them on the ground, that's the core of the so-called LOFA array, the low frequency array in Europe, led by our Dutch colleagues. And you see these elements are lying on the ground and looking at the sky at the, completely all the time at the same time. And so I have this little animation here, really demonstrates the power just by combining your signals electronically and providing sufficient software and compute power. You can have multiple beams on the sky at the same time, looking at vastly different objects like pulsars and galaxies, or if something goes up in the sky, you can move a beam, not from a pulsar, but from some galaxy away, and then look at this newborn star, for instance. And that is really a way we change astronomy. Or you can take the same kind of idea, and rather than putting your things on the ground, you put them in the focus of a radio telescope. And then you basically have a multi-pixel camera at the center of what used to be a single pixel camera, by having now the ability to move slightly away from the optical axis of your telescope, and that increases your field of view by an order of magnitude or more, and that allows you to capture more photons from different directions on the sky as well. Here, for instance, you see such a phased array, a path installed in the Effelsberg telescope in Bonn, where we use to observe, for instance, past radio bursts with it. It's really like having multiple telescopes looking at slightly different directions, and it really increases your service speed and how fast you can cover the sky, and therefore you're allowed to observe a little bit longer per pointing of the telescope. So it's really this new technology which allows us to have this huge increase in phase space. We can sample now large bandwidths, 50% fractional bandwidths are not unusual these days anymore. We can provide huge field of views, 30 square degrees or even much more. So that increases the service speed enormously. We can now have large frequency range. LOFA really has opened up the low frequency sky, and now other telescopes like MWA and others are really following suit. And of course, SKA low will also cover that range. And just a brute force increase in collecting area gives you better sensitivity, and all of it requires digital signal processing and, as we will see, huge compute power. But if you have that all in place, then you can make new science and new discoveries, and that's exactly what the SKA is all about. The SKA actually started, actually I should update the slide, I think it should be now 30 years or so. Started about 25 years ago with a really simple question. By the way, this is the new SKA logo, and I won't give you a lecture what I try to say with it, but it's quite beautiful. Anyway, the question on about the SKA really started about with a simple question. What telescope do you need? What size in particular is to answer how did the universe achieve its present form? What and where is dark matter? At the time, there was no dark energy yet discovered, so that didn't feature quite in the set of questions. How did galaxy forms? And what happened at the era that separated ionized from neutral hydrogen? And so hydrogen again comes up once more and again and again. And so that's why the first name, or one of the first names given to this new telescope, was actually not the SKA, but the hydrogen array. And Peter Wilkinson from Jodrell Bank was one of the first proponents of such an idea. And there are others at the same time. It was basically an idea born globally by various people, but I know Peter's work best, maybe because I'm from Manchester as well. And that's the conference proceeding that he wrote in 1991. I won't expect you to read all the details, but essentially he called it the hydrogen array. And he's already talking about a collecting area of 1 square kilometer, and already about neutral hydrogen observations for large redshifts, as well as even pulsar searching and pulsar timing. So he already almost had the key ingredients in that paper. And that's why I think I like this paper quite a lot, because there is really some foresight visible. But then it took some time for this idea to develop. And eventually we came up, or the community came up with the idea of the SKA. And rather than describing all the steps that went from this 91 paper to the concept that we have today, let me try what the expectations that we have from the SKA. We may not get them right away because we can build it up in phases, but that's of course the vision. The vision is that the SKA will be the world's premier imaging telescope. So we really want to take high quality snapshot images with great resolution. We want to do fundamental physics. We really want to be one of the physics machines of the 21st century. And of course, this doesn't go without having some great engineering ideas. The science cases, I use the plural here on purpose, is actually very wide. And the latest science book is actually coming in 2 volumes. There's a picture that I think Phil Diamond made. It really covers all the aspects and including all the questions that I've listened to you in the beginning of this talk. And of course, one thing also highlighted a lot by Peter Wilkinson in the past was the unknown. Really, the SKA, like many other telescopes, will probably be most famous for things we don't even expect to see right now. And the age of discovery in radio astronomy hasn't stopped. Fast radio bursts, which we still don't quite understand, is one of the nice examples where just recently we have a new field in radio astronomy just opened up by serendipity discovery that we didn't expect it before. Anyway, so this science book, I'm sure your favorite science cases in here. There are about 135 chapters. A lot of people on this call probably have contributed to this. And so it is, if you want to impress someone with it, this is really quite a nice document. Okay. As you will all know, a large fraction of the SKA is going to be built in Africa. At the moment, the core is in the Karoo in South Africa, but of course the hope and expectation is that the SKA will expand into neighboring African countries and even further away to get long baselines. And so we're really looking forward to that. And this is where the dish part of the array will be located. And on this Australian side, in Western Australia, sort of northeast of Perth, you're going to find this Christmas tree fire that will observe the low frequency sky continuously with about 100,000 or so of these antennas. And so together they form what we call the SKA observatory. The SKA observatory is in fact born. It is now officially a treaty organization, similar to CERN or ESO. And the location, the headquarters is at Jolly Bank in the shadow of the Lovell telescope. And from there, it will operate these telescopes in Africa and Australia. And the number of members are currently expanding. And in fact, Germany is negotiating, and we hope that we will join the observatory just this year. Of course, Germany has been involved in the SKA project for a long time, but so have been many other countries. And so hopefully the number of countries participating in this telescope will increase accordingly. But it is really not only a treaty organization, but there's actually hardware on the ground. You can see here a picture of the SKA little prototype. It's not a very large array yet, but it shows, it gives you a flavor how that will look in the desert in Western Australia. And of course, the real marvel right now is the MeerKAT array built by our South African colleagues, Sereo. It's a really beautiful, wonderful, world-class telescope. It's probably the best telescope at centimeter. Well, it's not probably, it is probably best. It is the best telescope around. It has beautiful imaging capabilities, and some on the call, I've seen Roger passing by. I have used it all very, very extensively. So it's a beautiful James as well. So it's really a beautiful telescope, and you can only congratulate our African colleagues to have been able to build this. It is really an honor to work with this telescope. And of course, for the SKA, it is the core. So we already have 64 dishes of the SKA on the ground, and we will be able to hopefully expand it very soon to have even more telescopes. With all these telescopes and all these antennas, there is a challenge. And this challenge is actually an interesting science project, apart from an engineering challenge in its own right. And that is really the huge amount of data that the SKA will produce. You have all these antennas, all these detectors, all these sensors producing data. And the data rate for SKA low is scary. It's 157 terabyte a second. Of course, you can try to combine the signals on site and reduce it, and you actually have to. But this will produce about 5 zettabytes per year. If you don't know what a zettabyte is, I had to look it up when I heard it the first time. It's 10 to the 18 bytes. So it's huge. The data rate on the SKA midsize is actually still pretty good. 2 terabytes a second is something that is scary, and that would produce unreduced 62 exabytes per year. I think I got zettabytes wrong. I think it's 10 to 21. Anyway, so the idea is that you have actually computers attached to the antennas or supercomputers, and they need about 130 petaflop operation speed. And the idea is that this will then boil down to about 300 petabytes that you'll try to store in your yearly archive. And the way we do this, or want to do this, is you really have to fast data reduction more or less online, right or near the antennas, or at least connected directly to them. And then you still have some pretty big data sets that you have to analyze further on. And I'm pretty sure, and I guess most of my colleagues would agree, that machine learning will be essential. In fact, we do this already at the moment. MeerKAT, for instance, we do a survey for pulsars. And in the past, we had PhD students sitting there going through the data. It's impossible. We capture about 2 petabytes a night. So we really need to deploy machine learning, and we do this quite successfully. But yeah, it is an engineering challenge, but it's also an opportunity. And I want to quote one politician here, Angela Merkel. She is a physicist, so she understands her business. She did point out, not quite with the same words, but in German, she expressed it in the meaning. She really felt and expressed it that algorithms and data are the economical resources of the future. So we like to dig up the ground and extract things from there, but the economy will be driven by data. And she's one of the many politicians who probably realize that this is the case. And so she must be right. So let's have a look at that. So this is just one data set that we want to look. This is actually a nice ASCAP, another SKA pathfinder telescope precursor. I'm not sure quite what the difference is anymore. But this is really multi-dimensional data cube, and you try to find the signature, for instance, here of an H1 galaxy. It would be impossible without actually having some heavy computing and additionally machine learning. It's really just a needle in a haystack. You really have to find your one galaxy, or maybe others, in this 1 petabyte data set, which is really quite a few pixels compared to a normal image that we had in the past. And because you can't really store this data, as you have seen, we really have to boil it down, reduce the data literally to a manageable data rate. This analysis has to be basically done in real time, which means you only have one shot. Or if this thing is, of course, not changing its properties in time, yes, you can reobserve and can redo the analysis. But if you think about time domain astronomy, pulsars, transients, and so on, then you basically don't have that choice, and you really have to do the analysis on the fly. The data volumes are huge even after we reduce them and bring them in the archives. And this is just one attempt to compare this with things that you may know. Of course, it's very scary to think that email is already a very, very large fraction, although I'm not surprised. Every morning if I look at my inbox, I can understand that this is probably a true number. But the point here is the raw data rate of the SKA is really comparable to the total internet traffic on the planet. And that just shows you the amount of data that we have to deal with. And even the amount of data that we want to put in an archive is something that rivals the LHC, the Large Hadron Collider, and CERN in its archive, in its high lumen upgrade in the future. And so it's not a surprise that CERN and SKA are talking to each other how to handle this data, how to manage them. And so here you can see, for instance, some news, which is already now 4 years old, but still interesting, that CERN and SKA have signed an agreement to actually cooperate on extreme computing. And the way we think it will work is we have these telescopes in the Australia and Africa, and then we have these data links to all the other regional centers in the world, and we have this reduced stepwise analysis of the data. And yeah, let's see if that really is happening. But from telescopes like MeerKAT, we already learn a great deal of how to handle this. So you already get a feeling that the SKA is not just an astronomy project, but it's actually an industry and technology project as well. And here are just some of the technology that are involved, not a complete list, but we want to build antennas, we want to build detectors, we need to transport the data, we need to have high performance computing, data management, storing. Renewable energy is becoming, of course, extremely important, even for mega science projects. So you don't really want to have a big CO2 footprint. So we really have to think about this much more than I think it is done right now. And infrastructure is, of course, maybe not very sexy, but actually important for any telescope to operate. The way it works is that countries who are a member of the projects get a fair amount of work returned in industrial contracts, returned to the country. They named this the Fair Work Return Principle. And it comes with opportunities, of course, for the member countries. But I have to say, it's also one of my biggest headache about the SKA, if I may say this so loudly, because for the project, it causes challenges. In my opinion, you don't necessarily get the best value for money by promising contracts to certain countries rather than competing globally around it. But I do accept that this is probably the only way to make countries participate in the project, because they're not doing this for the astronomy, they're doing this for creating jobs and opportunities. And so, but for the project as a whole, I think this is one of the big challenges that we really need to pay attention to, because we may spend more money and have less astronomy going this way. So this is something where I think the project of this size is not just a simple, we give the contract, we build it. No, there's much more politics behind, a lot of horse trading and so on. And I think that is probably the biggest challenge, not only of the SKA, but any project of that kind. But it's worth keeping this in mind. As I said, Germany has been involved in the SKA or radio astronomy for a long, long time. And we have been involved, or at least my predecessors have been involved in SKA working groups in the 90s. I joined in 99, just after I moved to Manchester. And then when I went back to Bonn, and that's now about 10 years ago, we felt, how can Germany contribute specifically to the SKA? And one opportunity that had arisen in the last years was that we can actually provide a prototype dish of the antennas that will make up the SKA mid-array. And so you see here the SKA prototype dish as designed by a German company, which, by the way, also designed Effelsberg, the Vanat-Meter telescope that is still operating very nicely today, in collaboration with Chinese colleagues. And this dish, as you see here, has been constructed with the help of our surveyor colleagues on site in the Karoo. And the idea is that, of course, after the testing is done and the prototype design has been confirmed, we will actually use the telescope for doing astronomy. It's a very nice, very quite sensitive telescope. It's not as big, so it can't be as sensitive as Effelsberg, but it's a really nice telescope, and we will do a cosmology survey measuring the foreground for this cosmic background, so we can help correcting for instance, the Planck maps. And we will do time pulsars, and we look for fast radio bursts. And so there's a lot of science just with a small dish that you can do. The antenna will also be probably the antenna type for the MeerKAT Plus array. That's an extension of the current MeerKAT array that we do in collaboration with Surveyor and also now Italian colleagues. So we will try to improve the sensitivity as well as the baseline, and hence the sharpness of the images of MeerKAT. And Roger has been very much engaged in Roger Dean, that is, in getting the science case for that together. So I'm looking forward to that in the next coming years. I want to finalize my talk by saying, coming back to the astronomy. Now I've been basically, I gave you the questions at the beginning, and now I want to say a little bit about how we try to answer them. I can't give you the full science case or pick only a few, and I have to sort of shorten the way how we get to the answer, but I hope I gave you at least a bit of an impression how we may do this. This is our home, the Earth, at least that part that shows you where I live. It's always scary how bright Europe is. You don't see much of a night sky, unfortunately. But never mind. But the Earth is only one of a number of planets in the solar system. And as you know, we have the rocky planets in the inner part of the solar system and the gaseous planets on the outer part. And we probably believe that life has to evolve on a rocky planet, or maybe on a rocky moon around a gas planet. But the idea is to understand how do these different planets form, and if possible, could life be there? So how do they form? We think there is material accumulated around a star. We call it a protoplanetary disk, but actually the process, how you sort of condense these dust particles to actually form, get together and form bigger and bigger entities to actually form rocky planets, is not yet very well understood. However, the observations are now in the optical, but also in the radio, getting there and trying to start understanding these processes. And here's a beautiful observation that was the first of its kind with the ALMA telescope at relatively high frequencies, capturing such a protoplanetary disk. And it's very interesting to see these rings, these gaps of dust. We believe that these are the places where the planets scoop up the dust and form. And so the idea with the SKA is probably somewhat higher frequencies than at the beginning, is that eventually the SKA will try to make movies that really show how these protoplanetary disks form, and leading eventually to the formation of planets. Of course, as I said, we have these rocky planets, we have these gas planets. If they're close to the star, we call them central star, we call them hot Jupiters. If they're far out, we call them cold gas giants. But really looking forward to the sort of the Earth-like planets that we believe are the foundation for life. And the SKA would have the sensitivity, at least for the most nearby stars, to pick up radio chatter or airport radar or some other leakage radiation that we leak all the time into the universe, to maybe be able to find the signature of civilized life somewhere. Or intelligent life. I'm not sure we have intelligent life on Earth, but well, at least civilized. Well, there's some technology. Or much more likely is that the SKA will actually be also a nice discovery machine for detecting new molecules that may be related to amino acids, and hence molecules that are related to biological life on some planets. And so that could be another way of finding life somewhere out in the universe. So the SKA, again, this is probably at somewhat higher frequencies than we start with, but that's certainly a tantalizing opportunity for the SKA to do in the future. The other one I already mentioned that the SKA will certainly have some contribution to is the understanding of dark matter. The idea of dark matter is quite old, 100 years already, where basically Kaptein in the Netherlands and Zwicky, I think already in the US at that time, pointed out that there may be some matter that we can't see. And in fact, we have not yet directly detected it, but we can indirectly see that there is some matter that certainly has some influence on gravitational interaction. And so for one of the most important and clearest examples, and the earliest example, in fact, was when people tried to measure the rotation speed of a spiral galaxy, for instance, and compared that speed as a function of distance from the center. In a normal galaxy, quote normal, if all the matter that you see it's all that there is, the rotation speed would increase the distance to the center, and eventually it would turn over and the speed would go down again. That's what we would expect if the light would all be the matter that we see. But what is actually observed is that the rotation curve continues to rise and then flattens out and never goes down. And so that is one of the first evidence for, oh, by the way, this is in German, sorry. The first evidence for dark matter. We also now observe gravitational lensing and dark matter clumps. We see the impact on the large scale structure. I show you a nice animation about that later on. And there's impact on the dark matter on the cosmic microwave background. So there's a lot of, it's not only the rotation curves that we have for the existence, pointing towards the existence of dark matter, but there's more. But going back to the rotation curve, this is basically what happens in a sort of expected normal case. You would have fast speed in the center and slow speed outside. But what we actually observe is that the speed is actually quite constant as a function of frequency, function of distance to the center. And the question is, what is this matter that changes the behavior of the visible matter that we can detect? So that's one unsolved question, and it may be a particle, it may be some strange new physics or axioms or whatever. But it could be something else. Some people have proposed it is a deviation from our understanding of the gravitational laws. Maybe. And here we have now another phenomena discovered at the end of the 90s, which is called dark energy. And dark energy is an unexplained form of energy. It really causes apparently the universe to expand more quickly in recent times, recent in quotes. And the way this is sort of displayed in an animation is you have the Big Bang, everything expands and expands and expands, and then eventually you would expect that the universe runs out of steam, but no, suddenly it starts to expand further. And that is strange. It's like throwing a ball into the air, and you would expect that the speed of the ball slows down and comes back. No, what actually happens, suddenly the ball continues to rise even at farther speed. And that's strange. That is, we don't understand this, and when we don't understand something, we call it dark something, in this case, dark energy. And so if you actually try to come up with how the universe is made up, you find that this dark energy, in terms of energy, comprises more than 70% of the universe. Dark matter comprises a little bit more like 20%, and only 5% or so are made of the atoms or material that you see around you. So in other words, we don't understand 95% of the universe. And hopefully the SKA can help with that. It's interesting because dark matter attracts while dark energy repels, and it's like a cosmic tug of war between the dark matter, which tries to help putting the universe together, and the dark energy, which eventually tries to pull it apart. And there is actually an understanding from particle physicists that this could be what they call vacuum energy. But the difference in vacuum energy that the particle physicists calculate and that we infer from astronomical observation is huge. It's a one with many more than 100 zeros difference. And so this is not just a simple calculation error or an uncertainty. This is a fundamental flaw in understanding the physics that we deal with. You can explain this in terms of general relativity if you invoke the so-called cosmological constant, but the difference to the particle physics numbers is still huge. And I like this because this is what The Guardian once entitled the battle for the universe. It's really, relativity has described the universe very successfully on large scales, and quantum mechanics has described the universe very successfully on the smaller scales. And yet both theories seem to be incompatible. And trying to find this theory of everything, the unification of gravity and quantum mechanics is still probably the hardest problem that physicists face today. But understanding what dark energy and dark matter is can help to actually solve that question. And so I come back to the same evolution of the universe in a slightly different graphics here. Again, we have the Big Bang. Then the universe was hot, it was ionized, and cooled down eventually. It was so cold that nothing existed apart from clouds of neutral hydrogen. So this is a signal that we can pick up with the SKA as a sensitive radio telescope, because this is exactly the kind of signal only radio can pick this up. Because this is the only signal that actually emerges and nothing else was there. Then they clumped together, these hydrogen clouds, and formed the first stars and galaxies, and they radiated, they ionized the universe. And we call that the epoch of re-ionization of the universe, from the first ionization to the second ionization. And we have all these galaxies and all these beautiful structures formed, and that we see today. And the nice thing about astronomy is the further the thing is away, the lower the frequency, we call this redshift, the further it is away in space and time, the lower the frequency. And so the lowest frequency, hence radio, allow you to go really back to the earliest observable parts of the universe. And so by studying the neutral hydrogen signal, how it evolved from this neutral bond to somewhat suddenly becoming ionized as the first stars appear and piercing holes in this neutral hydrogen in this nice animation here. This is by observing the different frequencies across the SKA band, we can try to pick up the signal and how the universe actually becomes as ionized as it is today. So the SKA will be able to trace the signal of the hydrogen as it will be ionized by the first stars and galaxies. Dark matter is also very interesting because we can try to, and dark energy, in fact, you can't really separate the two here. You can look at the structure that we observe and how it changed as a function of time. How did the universe expand? Because that gives you this feeling for this tug of war between the dark energy and the dark matter. And this is a beautiful simulation. I think it's a Millennium simulation or not TNG, I'm not quite sure, where you see on the left-hand side, so to speak, with an optical astronomer or a normal astronomer, and if we had our dark matter goggles on, you would see this structure here. And I'll let this animation run because I think it's quite beautiful. Oops, got stuck now. Nope, let's try again. Okay, you can see, so these are the yellow bits, so the violet bits are all dark matter, and where they come together in some knots, some galaxies form. And so if you had dark matter goggles on, you would see all this beautiful structure, but we don't. So we really have to infer the dark matter structure by just looking at the normal or astronomical objects in the optical, but also in the radio. And so by following this, we hope to thank you. We hope to understand what the main nature of dark matter and dark energy is. And the final example I want to give you is relates to my own science. Basically, it is actually related to how galaxies form. And galaxies, as we observe today, the big ones in particular, like the Milky Way, Andromeda, and so on, but also large elliptical galaxies, we believe that they have been formed by the merger of small galaxies. It's like a tree where the small ones form bigger ones, and the bigger ones form even bigger ones, and so on. So from small, make big as a function of cosmic time. And in fact, this merging of galaxies can be observed. And here's a beautiful gallery of HST images, where you basically have galaxies in the process of merging. It goes very, very slowly, so we can only capture the sort of a snapshot of that. But if you had a way to speed this up, then this may look like this. So let's say you have two spiral galaxies forming. You see a picture like this. You have some other galaxies merge, and then you take a snapshot to get a picture like that, like what we observed, and so on. So you have a number of simulations that can really reproduce these snapshots that we observe with our current telescopes right now. And this is a comparison between the simulations and the actual observations. This is actually still happening today. The Milky Way is on collision course with M31 Andromeda. And in about 2 billion years, these two galaxies will collide. M33 may also be in the mix. But currently, we're speeding with a speed of 430,000 kilometers an hour towards each other. And yeah, and the 2.5 million light years separation will be probably crossed in some 2 billion years ago. So it's not a problem that we have right now. But what is going to happen is really that these two large galaxies will merge. And actually, most of the time, nothing really happens, that you don't feel much, so to speak, because the space between stars is actually quite empty. But in the center of the galaxies, we'll have two massive black holes. Well, the one in the Sagittarius star in our galaxy is not that quite massive, but nevertheless, we have some very big black holes orbiting each other. And when they do this, like here, then they produce gravitational waves. And it's that kind of gravitational waves that we're trying to pick up, for instance, with pulsars in a so-called pulsar timing array. And of course, we have LIGO and Virgo and other ground-based detectors trying to capture gravitational waves as they propagate through the Earth, through the detector. And when a gravitational wave does that, it changes the length, it changes, it increases and decreases the length in this L-shaped interferometer. And using lasers, you can measure the difference in the length in both directions, and it allows you to detect gravitational waves. With pulsars, we can do exactly the same thing, but on a galactic scale. Here, we don't have mirrors and lasers, but we have pulsars, the Earth, and the pulsar signals. And as the pulsar signal propagates from the pulsar to the Earth, that time, the distance, changes slightly if a gravitational wave passes over this Earth pulsar system. And so the Earth is basically jiggling and changing the length scale, the difference, and that affects the arrival time that we can measure. And we can already do this quite successfully, relatively successfully, because we haven't made a detection yet. But we already have a sort of precision, an average precision of about 50 meters over 1 light year, which is pretty good. But for a fact of 2 or 3 words that we need to make a detection. I'm quite confident that we'll get the detection done with our current telescopes and maybe MeerKAT. But with the SKA, we can actually have so much precision that we can study properties of gravitons and localize the sources and so on. And this is my last slide. So I hope I could give you a little bit of an impression about how the SKA can help in answering those big questions that we sorry, just did mute. Now I can't get this window away. Anyway, I hope you can see the slide behind it, because I can't really see it. But anyway, I hope I could give you an idea about how the SKA can shape the answer to these questions that I mentioned at the beginning. I really think that MeerKAT will be a true trailblazer in making headways in answering these questions, not only in technology, but also in science. And in order to achieve the SKA and its full potential, we do need some scientific technological breakthroughs. And the challenges are here, as I mentioned, particularly the data and also data transport. But once we overcome them, then we hope to be able to answer these questions. And yes, and the nice thing about the SKA, what I really like about it, is that it's obviously modular. You would know you can always expand it, you can always make it better. It's not like a big optical telescope, for instance, where you build a big mirror and that's it. Here you can add more dishes, you can expand, you can go across Africa, you make the resolution even better, you can improve the sensitivity and so on. There is no limit, apart maybe from the cost and whether additional dishes will really expand the science case. Let me finish with, this is a plot where we simulated the expected discovery of pulsars with the current surveys that we do with MeerKAT. And as I mentioned before, the data rate is so high, we really have to do machine learning on the fly to analyze our data. That is challenging, a bit scary, because we can never go back. Well, we can verify by going back and testing the pulsar. But the machine learning has to work. If you miss that signal that we haven't trained it for, that would be unfortunate. But it shows the future. It shows what the SKA will have to do. And so with that, I hope I gave you some interest in following what the SKA will do in the future. And I'm certainly looking forward to get there. And I'll try to stop my screen now to get my control back. I'm not sure how to do this. Oops. I lost control over Zoom here because I don't know, now I'm painting. Interesting. Let me. No one else is the host. That's a problem. Okay, maybe while I do this, maybe I resume share. I need to go out of the stop share mode. By magic. Thank you very much. I hope yeah, I hope I whetted your interest, and thank you very much.
Well, thank you, Michael, for that excellent talk, emphasizing both the revolutionary science and the revolutionary technology involved in SKA, and also doing two jobs at the same time, both delivering the talk and dealing with the technology of the talk, which is always a great feat. But as far as the talk itself is concerned, the content of the talk, the words challenging and exciting hardly do it justice, the SKA project. I'm sure many people here will have really been thrilled to see that Botswana's flag is there in among the participants in the project, as one of the African nations who will play a particularly important part through AVN to begin with. Anyway, I see that we've had something approaching 90 participants in this talk, which is really excellent. So we do have some time for questions before I ask the Deputy Permanent Secretary to give some closing remarks. So if you'd like to ask a question, then perhaps raise your hand, or unless we have everybody mute at the moment, or raise one through chat. We do have a couple of questions through the chat. I don't know, Michael, whether you can see those.
I can see chat. I also see hands raised by Corin and James, and I don't know what order you want to take them. Maybe
I'll leave it to you. I'll leave it to you then, Michael, if you want to.
Let's, while I try to read, maybe Corin can ask a question, and maybe I can do multitasking, but I can still.
Yeah, okay. Can you hear me okay, Michael?
Yes.
Great, okay. So yeah, fascinating, huge project. Having worked on Gaia for many years, our data rates are just nothing in comparison. And in fact, this is the base of my question. I mean, are there any major technological developments that still need to be made in order to handle the volume of data in an efficient way? Of course, you can always do, just not process it all, or not process it as well as you want. Or is it really just a question of throwing computer power at it?
In principle, of course, it's the latter. I think in principle, we know how to do it, but whether it's the most efficient way and the most energy efficient way is yet a question. So when the computing, particularly the central processing was designed, there was always an energy budget with it, not only a money budget, but energy budget. And I think we know we should do more processing if we could, but we're really limited. So what I really think, personally, I think we need this green IT, this green information technology aspect much more looked into. Also, we will be facing the question, there have been already some questions asked to some other mega science projects. What is your CO2 footprint? And throwing just compute power on it bad idea. Cloud computing will probably make up 30% of all energy consumption on the planet in the 2030s. That's just too much. So in my opinion, this is a real technology challenge that eventually we need to solve. And also I think the current instrument can only be the first generation of computing. I think we need much more improvement in that. Yeah. So, the receiver technology, I think this will solve the time. We will do that better. And the dishes, once they're built, they're in the ground, you can only add more. But the computing is really where you can improve not only the capability of the telescope, but also on the energy budget, I think, which will.
So is it possible that actually the deployment of extra antennas could actually be limited by that rather than by the hardware itself?
I think there's a fear, because if you add more dishes, you have more data to transport, you have more data to process, and eventually you have to ask the question, what is the price tag for this? And what is the energy price tag, the CO2 price tag for that? So I think we have to start looking into this question much more than we have done in the past. That's my personal opinion. At the moment, I think the SKA observatory is more concerned about getting things on the ground.
Yeah.
In long term, I think that is the real questions we have to answer. And I think we can be a lighthouse. I think we can be an exemplary project in trying to address these things. Because we can do a lot with computing, but so anything that you can do more energy efficient with computing will buy you a lot, I think, both in science as well as in an energy budget.
Okay, thanks.
I have James next on my list, Ellie.
Okay, Mike. Thank you very much, Mike, for the very good talk.
Thank you.
Just one question has been bothering me about the scale of SKA from the beginning of the conception, and with the change in the budgetary constraints. I think I was still doing a PhD when the big book was written, and people had all the fantastic ideas about what we could do with the SKA. And then we had issues with countries dropping out of the SKA, funding going down, redesign of the spec, re-evaluation of most of the engineering aspect of the SKA. Has anyone bothered to look at the science cases we felt could be achieved? I think it was written in 2011 or 12, almost 10 years ago. Is there a review of those science cases to see what is no longer achievable with the current specification of the SKA?
I think that's an excellent question. I think that needs to be done, obviously. I mean, we in Germany is not a member as yet, so I can't complain, but I totally agree with you. I think we need to be realistic. I mean, it's normal. It's normal that a project of that size go through what they call de-scoping, redesign, limiting the scope. So that's completely normal, because it's always at the end a money problem. But you're absolutely right. I think we need to revisit the science case in terms of what is still possible. For the raw sensitivity that you need for some of these science cases may not be there. But on the other hand, the good thing about the SKA, again, it's not that a decision is necessarily irreversible. So if you decide to build, say, less dishes, it can be fixed by adding more dishes later. It's not like when I shrink this 100-meter optical telescope to 38 meters, you won't be able to make it 100 meter again. But with the SKA, you can. So I think on one hand, I can understand the authors that they're focusing on getting started and getting things on the ground, and you build up to the budget that you have. But you're totally right. We need to revisit the science case. We need to revisit for what is possible for whatever the scoping has to be done. And in my opinion, it's my personal opinion, it's not sanctioned, I don't speak for the SKO. In my opinion is you should look at, for instance, do you need all the receiver packages from the start? Maybe it's just you concentrate on a few receiver packages, but build more dishes. I believe, I haven't proven that yet, but probably you can do more science in terms of this original science case than by trying to provide a lot of frequencies right from the start. The problem is, of course, that people who will then suffer from these frequencies will be complaining, rightly so, no problem. And also, of course, this problem of fair work return. Some receiver packages have been promised to certain countries. So if they don't get the receiver package to be built, then they may threaten to drop out. So this is the problem with the fair work return. But at the end of the day, we have to be realistic. We have to start building somewhere. So I think that's what the observatory is trying. But I totally agree. We need to revisit the science case, and we need to make sure that the vision is still there. And I hope that's the case. I'm sure that for a number of science cases, that is still the case. But which one these are, we have to establish.
Okay, good. Thanks. Thanks for the answer.
No problem.
Michael, I think on the chat, there are one or two questions about the eventual merging of our galaxy with Andromeda, and questions about the effects of dark matter and dark energy on this. And then would people on Earth in a couple of billion years' time, what would the effects be there? So I think that hopefully that's preseeing the questions that are on the chat.
Giza has also a question later. I come back to that later. Yeah, I think the distance between Andromeda and the Milky Way is not that so huge, and the speed which we are approaching is relatively large. I think that outweighs the effects of the expansion caused by dark energy, even in 2 billion years. But to be honest, I haven't really asked that myself. So that's a very clever question. One should redo the calculation. But my gut feeling is that the effect of dark energy will be smaller than the relative than the effect of the relative velocity to each other. What effect it's going to be? For most of the path, we will probably not see quite a big change, unless, of course, when the galaxy comes towards us. If the solar system is still existing, which I doubt, then probably no collision with any other stars would happen, because the space between stars is just still very big. But depending where you end up, of course, in that merged galaxy, on which orbit you are, you may end up in the center of these two merged galaxies, and there the conditions could be quite different. And so I don't know. It's a fascinating science fiction story that you can write here, but I honestly don't know what the answer is. It's beyond my lifetime, that's for sure. So, but yeah, you can do some computer simulation as they have done, which are shown, and maybe track where the Earth will be following. But the space between the stars is still quite empty. So any collision would be unlikely, but it may be quite bright, depending if you end up in the center of these merged galaxies or not. I don't know if that answers the question, but I hope it does. Giza, is this how I should pronounce you? Sorry.
Yes, thank you. I would like to thank you for the nice presentation. It's really an enlightenment. You talked about radio astronomy, which can look at from centimeter to meter. Could you explain what that means in terms of temperature of the part of the universe that you are looking at, what the centimeter range goes to, and the meter range temperature? And the second question is, maybe it could be silly, but you talked about the volume of your data in terms of 3 dimension, and I'm wondering what that 3 dimension means. I mean, when you do this receiving the signal, yeah, you are looking at the space, but I'm a bit confused how you can look at it, because I'm not in that area. So I want to know how you can define this 3 dimension.
Not quite understand the last question about which 3 dimension you're talking about exactly.
The data volume you mentioned.
Data volumes. Oh, right. First of all, the first question, it depends, of course, exactly on the frequency range. You can use the Wien's displacement law to calculate it. But we're talking about basically of tens to hundreds of Kelvin if it's black body. But of course, the photons we observe, they may also come from a synchrotron emission or some other relativistic or non-thermal process. And then, of course, you can assign so-called brightness temperatures to that. And for instance, for pulsars, we see brightness temperatures of 10 to the 30 Kelvin. So it's really the whole range, depends really on which emission mechanism we are talking about. So there's no, I mean, that's the nice thing about radio astronomy. We are picking up a lot of non-thermal emission where you can't really assign a temperature to, at least, I mean, formally you can, but it just gives you a feeling for whether it's a coherent mechanism or incoherent mechanism and so on. So I don't know if that answers the first question as you would expect it, but it's really depending on the source that you look at when we talk about the involved temperatures. But in principle, we talk about tens or hundreds of Kelvin. As it comes to this to the dimension, well, the data that we take is actually quite complicated. It has certainly frequency information. It has spatial information. And of course, since we are
not
try to mute, but I can't be. I'm not so quick. All right. Okay. The dimension can be very high, and we have frequency resolution, we have time resolution, we have spatial resolution. And of course, then we also have, in principle, data from every single telescope that we connect together. We call it UV data, so which contains decoded spatial information. So it can be a multi-dimensional data cube, and the object you will try to find in this data cube is defined by what you find, what you want to see. But in principle, you can think about it as a 5-dimensional parameter space, for instance. And dimension is actually not the problem. The problem is really the amount as such. And the higher the frequency resolution, the higher the time resolution, the bigger the data set becomes. And there you need to find the needle in the haystack. And just thinking about a big cube and not so much about the dimensions, it makes the algorithms maybe more complicated, but not the managing of the data as such.
Okay. There are 1 or 2 other questions on the chat, but I think because time is going on, if you're happy to receive emails from those people, Michael, and just answer them offline, I think that may be the best thing. The one thing that has been asked is whether your talk could be made available for people to download the slides.
Sure, I can prepare a PDF version and put them somewhere on Dropbox or something. Yep, I can certainly do that.
Okay.
And what I can do, I can send all of that, including the recording, the link to Greg, and then Greg can distribute it to whoever is interested. And that is probably the easiest way of organizing it.
Yeah, that would be perfect. And the other question is from one of the participants, I think a Turkish ambassador, is the best source of reference for SKA, just for an overview, is that the website, would you say, or?
Trick question. I actually don't. As a source of information, I find the website not the best. Oh, I shouldn't have said this. I will now be in trouble. But yeah, it's certainly a good start. It's certainly a good start. I think the problem is the project evolves so rapidly. I mean, if you just Google it, you find so many information that is maybe outdated. So in terms of trying to be on top of what's the current thinking, the website is probably the best starting point. And then you can branch off from there, I think. But there is actually, maybe what they have produced is a very nice glossy brochure, which encapsulates the SKA quite nicely. I think that's a very nicely done brochure, much more concise than trying to find information on the website. We can perhaps put a request to the office to provide a few copies of those and distribute them to people interested. But you also may be able to download the PDF file. I haven't checked, but the PDF file may also be available on their SKA website, which is skatelescope1word.org. I think that brochure is actually very nice. So they did a very nice job there.
Okay. Thanks, Michael, for that. And I would like finally to invite Deputy Permanent Secretary, Dr. Baipaledi in the Ministry of Tertiary Education, Research, Science and Technology to just give a few closing words.
Thank you very much, Mike. Now I'm going to be talking about Mike as well. But thank you very much for chairing the meeting, Mike. And I will make my little remarks in the sense that I recognize the presence of the Vice Chancellor. I hope he's still there, Professor Totolo. And of course, Professor Michael Kramer for your presentation this evening. And of course, Professor Michael Bode as a visiting professor of astrophysics to BUST. Distinguished guests, colleagues, ladies and gentlemen, students, my role this evening is to offer closing remarks at the end of this mind-probing presentation by Professor Michael Kramer from Max Planck Institute in Germany. A few days ago, media was abound with the uncontrolled crash landing of a 22-ton satellite that crashed into the sea near one of islands. And this just goes to show how developed and developing countries continue to invest in new technologies and advancements. Program Director, my reference to this slight mishap is to demonstrate the immense investment and the drive by some countries to remain at the helm of making groundbreaking discoveries on space. The presentation by Professor Kramer this evening has further demonstrated and shed light for career opportunities that remain untapped to the developing countries and thus presenting opportunities for universities to develop programs and studies to enhance courses that align to new and emerging markets. And I was impressed when Professor Kramer said, even if you're going to search the information, you might not find the latest information on SKA, even though it's there, but it's not latest. So you need to keep up with the development and changes that happens on this space. Program Director, Professor Bode, I also want to urge our universities to begin to take their place to drive the market and not being market-driven. Universities must undertake groundbreaking research in order to remain relevant and attractive to partnerships. To students, to remain relevant to partnerships, to students, and the market. The amount of knowledge and findings therein will lead to new economic pursuits and new markets. Talks like this one by Professor Kramer and many other talks in the past should provide and serve as a kaleidoscope for reaching impactful decisions and life-changing career paths for our universities and our economy. In conclusion, I want to thank and appreciate the talk made by Professor Kramer and urge the Botswana International University of Science and Technology BUST to enhance their ties with Max Planck Institute on radio astronomy. I am aware that negotiations between your institution and BUST are at advanced stage where an understanding will be formalized to assist Botswana with developments around radio astronomy and human capital. As the government of Botswana, we are grateful for the steps the German government continues to take in development initiatives in Africa and Botswana in particular. We look forward to more symbiotic relationship with yourselves. I also want to thank the BUST management for their continued engagement with reputable researchers and scholars across the globe in pursuit of human capital development and inspire youth towards new careers and opportunities. Ladies and gentlemen, the benefits for any nation to pursue the space science and technology agenda are limitless. We hope as a government to have generation of scientific knowledge, diffusion of innovation, improvement of our day-to-day lives, and sparking youth's interest in the area of STEM. Lastly, let me thank you for your attendance today and implore you to be game changers. Through concerted effort, we can begin to see the world as a better place for all who live in. And I'm very grateful that almost 100 participants attended this presentation today. Thank you very much, Program Director. Thank you, Professor Kramer. If you're in Botswana, we'll take you out to go and taste our cuisines here and enjoy our beef and our dance. Thank you very much and good evening.
Thank you.
Thank you very much, DPS, and thanks to everybody, distinguished guests and so on, for attending this talk tonight. I think you, DPS, said everything that needs to be said to sum up what we've heard tonight and the way we see things developing into the future. So with that, thanks again to Michael. Thanks everybody for joining, and keep safe, stay well, and thanks again.
Thank you very much.
Thanks, Michael.
Thank you very much.
Thank you, Michael. About the next band.